Where do we live? And I don't mean where do we live in Cambridge or in Massachusetts or the United States or even on Earth, but where do we live in our Milky Way galaxy? And why don't we know the answer already? We've observed hundreds of millions of galaxies in our universe, and for those that lie nearby, we can obtain exquisite maps of their structure. However, we have no such map for our own home galaxy, the Milky Way. Rather, we only have data-driven models or artist conceptions of what we think our galaxy might look like from the outside. That's because our solar system is located about halfway out from the center of our Milky Way, as depicted in this bird's eye view, seen from above. And it lies deeply embedded inside our galaxy's pancake-shaped disk of material, when depicted in this edge-on view, seen from the side. As a result, we will never have the benefit of a true face-on image like we have for those external galaxies. We must map our Milky Way from the inside out. This is very challenging, and even today, many fundamental questions about our galaxy structure remain unanswered, which have implications for how galaxies, and stars like our sun within them, form and evolve over time. My name is Katherine Zucker, and I'm an astronomer, specifically a galactic cartographer, focused on developing novel techniques to tease out the true 3D structure of our Milky Way galaxy. Specifically, I set myself the goal of producing the most accurate map of star-forming regions in a part of our galaxy called the solar neighborhood, or the nearest few thousand light years from our solar system. In this artist conception, the star-forming regions are shown as pink-red splotches, which I've marked with red pushpins. We can think of star-forming regions as the regions of new construction in our solar neighborhood. Stars, and planets like our Earth, are born in star-forming regions. We can also use star-forming regions to trace out our galaxy structure because they act as beacons, which can delineate its characteristic spiral pinwheel pattern. In order to map out the distribution of star-forming regions, we need to know how distant each region is from our sun. Distances are very difficult to obtain, however, because star-forming regions are not solids, but rather dynamic nebulous clouds of interstellar material, containing what astronomers call gas and dust. So, how do we obtain distances to star-forming regions? Well, consider a sunset. Recall how the light from our sun appears redder as it dips below the horizon. Our sun's light is not naturally this red, but just appears so from our vantage point. This is because as the light from the sun travels through our Earth's atmosphere, the shorter wavelength, blue light, is preferentially scattered by small atmospheric particles compared to the longer wavelength red light. We can think of this same effect, called reddening, occurring throughout our Milky Way galaxy. So, instead of the sun, let's consider a different star, far, far beyond our solar system in the Milky Way galaxy. Imagine that we know that this star would be green if we observe it with nothing in the way. Now imagine there's a bunch of dusty, cloudy stuff in the way, a star-forming region. The small dusty particles in that star-forming region will redden the light from this green star, just as the Earth's atmosphere does to the sun as it sets. Now, consider many such green stars scattered throughout the cloud in 3D, and consider how the light from those stars will be reddened by the dust cloud, and how that will affect the color of each star. Now, if you have a very advanced statistical framework, and you have a lot of computing power, you can self-consistently infer the colors and distances of the stars themselves. And in doing so, you can also infer the distance of the cloudy, dusty, nebulous material, the star-forming region, that is producing this effect. And your error bars improve significantly if you have independent constraints on the star's distances, as we now do have due to the recent launch of the Gaia space mission. The result, a cornerstone of my thesis, is the largest and most accurate map of star-forming regions in the solar neighborhood ever produced. So, let's take a look at this new map, which looks very different from what we anticipated. Each red dot shows a blob of star-forming gas, a star-forming region, whose distance from us has been accurately measured using this reddening technique. These star-forming regions are not randomly distributed, as suggested by the pink-red splotches in this artist's conception. Rather, they connect to form a gigantic structure. This 9,000 light year long structure is sinusoidal in shape, with an amplitude of about 500 light years. We call this structure the Radcliffe wave, as it was born out of a collaboration at Harvard's Radcliffe Institute. At its closest point, the Radcliffe wave lies within just 500 light years from our sun. Nobody predicted that we lie next to a giant wave-like collection of interstellar material, and its existence is forcing us to rethink our understanding of our galaxy structure and the processes by which stars form within it. So, what does this mean for you and for me? My work will help usher in a new era of data-driven models and poses new questions for what could cause this wave-like ripple in our solar neighborhood. But for now, we can say that we know where we live in our Milky Way. Thank you.